In Chapter 6, we're going to talk about exponential and logarithmic functions. But let's start out by talking about exponential functions. An exponential function has this basic form. Y equals A times B to the power x. In an exponential function, the variable is an exponent, where A and B are numbers known as parameters. The domain of an exponential function is from negative infinity to positive infinity. The range of an exponential function is from 0 to positive infinity. But note, when we make transformations, this can change. Exponential functions fall into two categories, growth and decay. A growth function is when the parameter b is greater than 1. A decay function is when the parameter b is less than 1. A growth function typically looks like this, whereas the decay function typically looks like this. Now we'll explore some features. If I have some exponential function, y equals a times b to the power of x, the y-intercept is when x is 0. So an exponential function has a y-intercept of a times b to the power 0, but recall from Algebra 1, anything to the power 0 is equal to 1. So the y-intercept of an exponential function is a. Exponential functions also have what's called a horizontal asymptote. The horizontal asymptote of an exponential function is the line y equals 0. Note, if we perform transformations, this can change. So if we shift the function up, down, left, or right, or up or down, the asymptote will change. So now, here's the general form. The base is b. So the base of this particular exponential function, well, this is just like writing y equals 1 times 2 to the power x. So the base for this exponential function is 2. Since b is greater than 1, this represents a growth. And since we have not made any transformations, the asymptote is y equals 0. In this example, again, a is 1. We can write this as 1 times 1/2 to the power x. This is b, also known as the base. So in this example, the base is 1/2. Since the base is less than 1, this represents a decay model. And since there are no up or down transformations, we haven't talked about those yet, the asymptote is y equals 0. Exponential functions are very useful in modeling real-world behaviors. Generally, the growth model will be of the form y equals a times 1 plus r to the power of x. Note, all we have done is replaced b with 1 plus r. For a decay model is very similar. Y is equal to a times 1 minus r to the power of x. Again, all we have done is replace b with 1 minus r. So in a real world scenario, a would represent starting value. And that's because that's our y-intercept. R would represent the rate of change. Typically, R is going to be a percent that has been divided by 100. So for example, if the rate is equal to 5% growth, then our function would be y equals a, which would be the starting value, times 1 plus 0.05 to the power x. What I've done is I've taken the rate, 5%, and divided it by 100. Let's look at an example. The value of a car, y, in thousands of dollars can be approximated by the model, y equals 25 times 0.85 to the power t, where t is the number of years since the car was new. Is this a growth or decay? Well, here, that is b. And since b is less than 1, this represents a decay model. What is the annual percentage increase or decrease of the car's value? In other words, they're asking us for the rate. Well, since b is equal to 0.85, and we've replaced b with 1 minus r, since this is a decay model, we are going to use 1 minus r. Well, I can just set these two equal. And that means that r is equal to 0.15. You just solve for r. So the annual percentage increase or decrease is 15% decrease each year. Now they're asking us to estimate the value of the car after 7 years. Well, they've given us the time, which is t. So all we need to do is plug 7 into the model to solve. So y equals 25 times 0.85 to the power 7. So we just plug this into our calculator. (25) times 0.85 to the power 7. So the value of the car after 7 years is 8.0. Well, 8.0 what? The value of y was in thousands of dollars. So this is valued at $8,014. Let's look at another example. In 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. Write an exponential model of the population, y, in billions, t years after 2000. Well, let's dissect this problem. 2000 had a population of 6.09 billion. This is the starting value. So A is 6.09. B is going to be, well, this is an increase in population. So this is a growth model. So B is going to be 1 plus R. And R is 1.18%, but we need to express that as a decimal. So we'll divide that, 1.18, we'll divide it by 100. So what is that then? And then we're adding 1. So B is 1.0118. So our model is y equals A times B to the power x, where A is 6.09, B is 1.0118 to the power t. So this is going to be our model. Notice that B is greater than 1, which means this is a growth model. So now, estimate the population in 2005. Well, T represents the years after 2005. So for this case, T is going to be 5, because 2005 is 5 years after 2000. So our population is going to be y equals 6.09 times 1.0118 to the power 5. So we'll plug that into our calculator. And the population is 6.4578. And we'll use the same number of decimal places, too. So we'll round this to 6.46. So the population is 6.46 billion. Now let's estimate the year when the population was 7 billion. Now let's just find we'll round it to the nearest year. So let's just use our calculator for this. Well, let's just copy this same formula. In 2006, the population was 6.5 billion. So let's just pick a bigger number for x, or t rather. How about 10? We're getting closer. Remember, we're trying to find an x value that will yield a number close to 7. Let's try 15. Okay, I went too far. So we'll just keep guessing and checking. That's pretty close. Let's go down by 1 more just to see if I can't get even closer. All right, so that is too small. So when x is 12, our population is just over 7 billion. So in other words, in the year 2012, this question is really just a guessing and checking problem. Now let's take a look at some interest formulas. The most commonly used interest formula is A equals P times 1 plus R over N to the power N times T. All right, let's unpack this formula. A, in this case, capital A, that represents the current value. P is the principal. In other words, it's the initial investment or the starting value. That says value, by the way. R, like before, is the rate or the interest rate. N is the number of compounds, and we'll talk about that in a moment. And T is the time. Okay, so now, what does it mean to be a compound? So that means how many times in a given period the interest is computed. So, for example, if interest is compounded annually, that means n is equal to 1 because the interest is computed once a year. If it's compounded quarterly, you guessed it, n is equal to 4. So that means 4 times a year, interest is computed. Well, what if it's compounded daily? Well, if the interest is compounded every day, then the number of compounds would be 365. Okay, let's look at an example. $400 is invested into an account. So this represents the initial investment. So that means P is 400, the principal. This account pays an interest rate of 3.8%. So that means R is going to be equal to 3.8 divided by 100. The interest is compounded monthly. So every month the interest is computed. So that means that N is equal to 12. So now they want to know how much money will be in the account after 11 years. So T is equal to 11. So let's set up the problem. A equals 400 times 1 plus 0.038 divided by 12 to the power 12 times 11. So let's go ahead and compute that. Four hundred times 1 plus 0.038 divided by 12 to the power 12 times 11. $607.17. We'll round that 16 to a 17. So the total amount of money is $607.17. You can imagine that the larger n gets, in other words, the more frequently interest is computed, the more money you'll make in a year. So interest that's compounded monthly is better than interest that is compounded quarterly, which is better than interest that is compounded annually. Let's take a look at another example. $3,900 is left in an account for 14 years. Okay, so this is the starting value. Oops. So P is going to be 3,900. it's left in an account for 14 years. So t is equal to 14. Assuming the interest is compounded daily, so that means that n is 365. What interest rate, so in this example, we need to find the rate. What interest rate would be required to end up with $9,200? So this is the final amount. Okay, so this is a problem that we need to solve. So let's set it up. A equals P times 1 plus R, which we don't know, over 365 to the power 365 times 14. Okay, so let's go ahead and start this problem. We can divide both sides by 3,900. And what is that? That's about 2.35. Oops. Now I'm going to go ahead and compute this little bit up here. 365 times 14. $365 times 14 is 5,110. So this is all to the power 5,110. Okay, so now I need to get rid of this exponent. So let's go back to where we talked about rational exponents. What we can do, I'm going to move this over just a tad. No. What we can do in this case is we can take the 5,110th root of both sides. Okay, so that means that 1 plus r over 365 is equal to, well, how on earth am I going to compute that? Well, so we'll take this number up here and we'll raise it to the power. Now recall that the nth root is the same as raising it to the power 1 over n. So I'm going to raise this to the power 1 over 5110. And I'll wind up with 1.000167. Okay, we're almost done. So I'll just subtract the 1. So this is 0.000167, and that's equal to r over 365. And so now we'll just multiply both sides by 365 to get our value for r. I don't know why this is purple. Now you'll notice I'm not rounding each time. I go up in my calculator, press enter to get this whole number. I'm going to multiply this by 365. So this is a very large percentage. Oops, nope, that's not right. I forgot to subtract the 1. So let's subtract the 1. That makes much more sense. There we go. Now we'll multiply by 365. Okay, so 0.061. Well, we'll just use 2 digits. Now we want to express this as a percent. So what interest rate? So we'll just multiply this by 100 to get our interest rate. And so when I multiply that by 100, I get 6.1%. So you would need to earn 6.1% compounded daily in order for that growth rate to happen. Okay. Now let's talk about the number E. The number E is a constant. It's a constant in nature that represents growth. Now, I'm not going to spend a lot of time talking about where the number E comes from, but it represents constant growth. It's a constant that represents constant growth. And E is approximately equal to 2.71828, etc. This is a decimal that goes on forever. E is an irrational number. Think of it as being like the number pi, which is approximately 3.14159, etc. E is just another constant that exists in nature, and this is probably the first time you've been introduced to it, but it is probably one of the most important numbers in math. It doesn't have a geometric representation like pi does. It's just a number that is fundamental to things that grow. Things like interest rates or the economy or population growth or the spread of viruses like COVID. E is used to model anything that grows. Okay, so let's look at an example. The continuous growth model is A equals P times E to the power RT, where E is the number 2.71828, etc. The number E is in your calculator. If you have a TI-84, the number E is right over here, just above the LN button. It's also, you can also look for it in blue above the division bar. Okay, so this is e to the x, and here is e above the division bar. So if you press second divide, you can get the number e. And if I press enter, there you have it, 2.71828, etc. And this is a decimal that goes on forever. So let's look at an example using e. Okay, so money is invested into an account that earns 5.6% compounded continuously. And this is the key word that tells you you're going to use the number E. So how much would need to be invested for the value to reach 78,000 in 9 years? All right, so let's unpack this. So here's our interest rate. So R is going to be equal to 5.6 divided by 100. So R is 0.056. How much would need to be invested? So in other words, we're looking for P. We're looking for the initial investment so that it reaches 78,000. That's the final value. And 9 years, that is T. So since this is continuous, we are going to use the formula A equals P times E to the power RT. So let's plug in the values. A is 78,000. P is unknown. E to the power R, which is 0.056 times T, which is 9. Okay, this whole thing right here, we can just compute in our calculator because E is a number. So we'll do the E to the power X. That button is right down here over on the left by the ln. So second ln, that will give me, second ln, that will give me E to the power 0.056 times 9. So that number is about 1.65. So this number right here was, what was it again? 1.655. So to solve this, we simply need to divide both sides by 1.655. And if you go on to take pre-calculus, you'll learn a lot more about E. And if you end up taking calculus, you're going to learn a whole lot more about E. So to compute this, we'll just do 78,000 divided by, and then I'm going to arrow up to copy this whole thing down. So our final answer is 47120 and 53 cents. So that's how much money we would need to invest in our account so that it grows to 78,000 in 9 years. That's all I have. Thank you for watching.